So let's take a look at representation of functions as power series. So let's say we have the function 1 over 1 minus x. Now the series for this is going to be from n equals 0 to infinity of x to the n. And so let's compare this to a geometric series. Now once again, in a geometric series, let's say we have from 0 to infinity of a times r to the n, where a is going to be the first term of the sequence and r is going to be the ratio taken to the n power. Notice how both of these series are geometric. And so x is basically going to be the r value. And the a value in this case is 1. Now in order to find the interval of convergence, remember that in a geometric series, the absolute value of r must be less than 1 for the series to converge. So in this case, the absolute value of x must be less than 1. In order to get rid of the absolute value, we can rewrite it as x has to be between -1 and 1. So we know the interval of convergence of this series from n equals 0 to infinity of x to the n has to be from -1 to 1. Now we can test these endpoints by plugging them in for x, but when we do that, remember we get -1 and 1 to the n power. But since x is equal to r, and the absolute value of r must be less than 1, if we plug in both -1 and 1, the absolute value will obviously be 1. And 1 is not less than 1, which means the series will diverge. So it does not include those endpoints. So we can leave it as it is. And if it did include those endpoints, remember we would have to put closed brackets like so. So let's say for number 1, we have f of x equals 1 over 1 plus x, and we're trying to find a power series and the interval of convergence. So what we need to be able to do with these is to find a similar function that we know the series of, use substitution, and then evaluate. So we know the series of 1 over 1 minus x. Obviously, once again, that is going to be from 0 to infinity of x to the n. But in this case, we have 1 over 1 plus x instead of minus x. So how could we change or manipulate this equation? Well, we could rewrite it. We could rewrite 1 over 1 plus x as 1 over 1 minus a negative x. So now that we have it in the form of 1 minus some value. And so now, notice instead of x, we have negative x. So all we have to do is look at the series, and everywhere we have x, we're going to replace it with negative x. So it's going to be equal to the series from n equals 0 to infinity of negative x to the n power. Or if I want to take out the negative, I can also rewrite it n equals 0 from infinity of -1 to the n times x to the n. And so that is the power series of 1 over 1 plus x. And so in order to find the interval of convergence, remember in a geometric series, if we go from 0 to infinity of a times r to the n, the absolute value of r must be less than 1 for the series to converge. So it might be a little difficult to look at this series and find the interval of convergence, so we can always switch back to just this one. Because we know that negative x is the r value, because that is the value that is being taken to the n power. So in this case, the absolute value of negative x must be less than 1. Now in order to get rid of the absolute value, we can rewrite it as negative x must be in between -1 and 1. And so if I were to divide over the negative to both sides, we remember when we divide or multiply by a negative, we must flip the inequality. So 1 must be greater than x, which is greater than -1. Or simply, x has to be between -1 and 1. And so we know the interval of convergence must be between -1 and 1. Now we can test these endpoints. So if I plug in both -1 and 1 for x, so if I go ahead and start by plugging in 1 for x, we'll get -1 to the n power of the series from n equals 0 to infinity. And remember, for a geometric series to converge, the absolute value of r must be less than 1. In this case, if r is a negative 1, the absolute value of negative 1, which is 1, is not less than 1, which means the series will diverge. And if I plug in 1 also, if I plug in negative 1 also in for x, I will also get 1 to the n, which means the series will also diverge. So I will just put open parentheses here, which means it will converge for all values of x between negative 1 and 1, and not including the endpoints. So that is the interval of convergence. So now for number 2, we have f of x equals 1 over 1 minus x cubed. So if we were to find a power series for this, notice how it is in the form of 1 over 1 minus x. And so the series for that, once again, from 0 to infinity of x to the n. But in this case, instead of having x, we have x cubed. So all we have to do is replace our x value with x cubed in order to find the series. So the series of 1 over 1 minus x cubed is going to be from n equals 0 to infinity of, instead of x, we have x cubed, so x cubed to the n power. Or I can rewrite it, because there's a power to a power, those multiply. So we have the series from n equals 0 to infinity of x to the 3n power. So now in order to find the interval of convergence, obviously x cubed is what's being taken to the n power, so x cubed is our r value, and so the absolute value of x cubed must be less than 1. In order to get rid of the absolute value, we can rewrite it as x cubed must be in between negative 1 and 1. And so to evaluate, I can take the cube root of both sides. The cube root of negative 1 is still negative 1. So then x must be in between still negative 1 and 1. So our interval of convergence is between those two values. Now we can test those endpoints once again, but similar to the last problem, if we plug both of these in for x, the r value will be 1. And remember, in order for the series to converge, the absolute value of r, which is 1, must be less than 1, and it is not. So that means it will diverge when we plug in the values of negative 1 and 1. So we cannot include those endpoints. So now for number 3, we have f of x equals 1 over x minus 5. So in order to manipulate this equation, I can actually factor out a negative on the denominator. So we have 1 over negative x plus 5. And then I can rearrange it so that we have, I'll move the negative up top. So we have negative 1 over 5 plus x. And so now what I can do is factor out a 5 once again from the denominator. So we have negative 1 over 5 times 1 plus x over 5. And so now what I'm going to do is move the 5 up top. So now we have negative 1 over 5 over 1 plus x over 5. And so for the final step, I'm actually going to move the negative 1/5 out front. So now that we have in the form of negative 1 over 5 times 1 over 1 plus x over 5. And so for right now, I'm just going to ignore the constant negative 1/5 and focus on what's inside. Now notice this is similar to 1 over 1 plus x. And we know the series of that because we did that in the first problem, from 0 to infinity of negative 1 to the n times x to the n, or negative x all to the n power. And so instead of having just x, this time we have x over 5. So all we have to do is, wherever we have an x, we have to replace that with x over 5 and evaluate. So I can rewrite this series as the series from n equals 0 to infinity of negative 1 to the n times, instead of x, now we have x over 5. So we have x over 5 to the n power. Now since we have a negative 1/5 as a constant, we can either put that outside the series or inside. So now when I include the negative 1/5, I can rewrite it as the series from n equals 0 to infinity of negative 1 over 5 times negative 1 to the n times x over 5 to the n power. And so if I want to simplify, I can distribute the n over to x over 5. So we have negative 1 over 5 times negative 1 to the n times x to the n over 5 to the n. So notice how 5, this is basically 5 to the first times 5 to the n. Since they do have the same base and they're being multiplied, we can add the powers. So I'm going to rewrite this as negative 1 times negative 1 to the n times x to the n over 5 to the n plus 1. So we have the series from n equals 0 to infinity of negative times negative 1 to the n x to the n over 5 to the n plus 1. Now also another way I can simplify is I can take this series I wrote on the top left and combine the negative 1 with the x over 5. And so we'll get the series from n equals 0 to infinity of negative 1 over 5 times negative x over 5 to the n power. And so now that we have it in the geometric series form, and so negative x over 5 is at r, we can find the interval of convergence. So the absolute value of negative x over 5 must be less than 1. And so the absolute value of negative x over 5 is obviously just a positive x over 5. And so if that is less than 1, in order to get rid of the absolute value, we must put it in between both negative 1 and 1. And so if I multiply by 5, we'll get that x must be in between negative 5 and positive 5. And so in order to test those endpoints, we can plug it in for x. So if let's say I plug in 5 for x. If I plug in 5, we'll get negative 5 over 5, which is negative 1 to the n. So we get negative 1 over 5 times negative 1 to the n, the series. And so if our r value is negative 1, the absolute value of r is equal to 1. And 1 is not less than 1, which means the series will diverge. And it'll work the same way if I plug in negative 5 for x as well. So that means x must be in between negative 5 and 5 for the series to converge, but it cannot include those endpoints. So I'll just use open brackets and state it like so. Now keep in mind, if you have it in this form, you can also use the ratio test, and you'll get to the exact same answer. So now for number 4, we have f of x equals x over 9 plus x squared. So what I can do here is factor out a 9 from the denominator. So we get x over 9 times 1 plus x squared over 9. And then I'll bring that 9 up to the top. So then we'll get x over 9 over 1 plus x squared over 9. Now similar to the previous problem, I'm actually going to bring x squared, or x over 9, and bring it out front and treat it similar to a constant. So we'll get x over 9 times 1 over 1 plus x squared over 9. And so if we ignore x over 9 just for a second, and we focus on the inside, notice the inside is similar to the function of 1 over 1 plus x. And we know the series of that is, once again, from 0 to infinity of negative 1 to the n times x to the n. But instead of having x, we have x squared over 9. So wherever we have x in the series, we're going to replace that with the value of x squared over 9. So the series is basically going to be from n equals 0 to infinity of negative 1 to the n. So instead of x, we have x squared over 9, so times x squared over 9, the entire thing to the n power. And don't forget, we have x over 9 out front, so we can just multiply it. So then we'll get the series from n equals 0 to infinity of x over 9 times negative 1 to the n times x squared over 9 and the entire thing to the n power. So now to simplify, I'm just going to rearrange the terms and distribute the n to both the numerator and the denominator. So we'll get negative 1 to the n times x over 9 times x to the 2 to the n, which is the same thing as x to the 2n, over 9 to the n. Now if I were to combine both of the numerator and denominator, we'll get negative 1 to the n times x to the 2n plus 1. So since they're the same bases, we can add the exponents. And then so over 9 to the n plus 1. So if I were to rewrite the series, we'll get the infinite series from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 9 to the n plus 1. So now in order to find the interval of convergence, it is kind of difficult to go back and use the geometric test. So what we can do is use the ratio test. So once again, for the ratio test, we're going to set the limit as n approaches infinity of x to the 2, and remember we're going to replace n with n plus 1. So we have x to the 2 times n plus 1 plus 1 over 9 to the n plus 1 plus 1, which is 9 to the n plus 2, over just our regular sequence. So x to the 2n plus 1 over 9 to the n plus 1. So the absolute value of the entire thing. And remember, we're taking the absolute value so we can always eliminate the alternator in the series. And we don't need to include that. And so if I am dividing by this fraction, I can multiply by its reciprocal. So I will multiply by 9 to the n plus 1 over x to the 2n plus 1. I'm just going to go ahead and erase that denominator. And so now what we have to do is just simplify and expand all these exponents so we can cancel out terms. So if I were to rewrite 2 times n plus 1 plus 1, I'll just rewrite it as x to the 2n plus 2 plus 1, which is 2n plus 3. So now over 9 to the n plus 2 multiplied by 9 to the n plus 1 over x to the 2n plus 1. And so now if I were to expand this, I would have x to the 2n times x cubed, which can just be written as x times x times x. We have times 9 to the n plus 1, which can be expanded as 9 to the n times 9 to the first, which is 9, over 9 to the n plus 2, which is 9 to the n times 9 squared, so 9 times 9, times x to the 2n plus 1, which is x to the 2n times x. So notice we can just cancel out a bunch of these terms. So 9 to the n's will cancel, x to the 2n's will cancel, 1 of the x's will cancel, and 1 of the 9's will cancel. So we're going to be left with the limit as n approaches infinity of the absolute value of x times x, which is x squared, over 9. Since we don't have any n's remaining, we can just eliminate the limit and set the absolute value less than 1. Because we know in a ratio test, if the limit is less than 1, that's where it converges. So in order to get rid of the absolute value, we must put it in between negative 1 and 1. And if I multiply both sides by 9, we get negative 9 is less than x squared, which is less than 9. And since we have an x squared here, x squared can never be equal to a negative number. So we can just eliminate that. And so we're left with x squared must be less than 9. So whenever we have x squared, we must take the square root, so x must be less than 3. And we also have to flip the inequality and turn it to the negative number. So x must be greater than negative 3 as well. So we know that our interval of convergence is from negative 3 to 3. And we can test these endpoints as well. So let's say I just plug in 3 for x into the series. So then we'll get negative 1 to the n times 3 to the 2n plus 1 over 9 to the n plus 1. Now I can rewrite 3 to the 2n plus 1 and expand it, and I can also expand 9 to the n plus 1. So then we'll get 3 to the 2n times 3 to the first, which is 3, over 9 to the n times 9 to the first. Now I can also rewrite 3 to the 2n as 3 to 3 squared to the n power, which is the same thing as 9 to the n. And so we get the series from n equals 0 to infinity of negative 1 to the n times 9 to the n over 9 to the n times 3 over 9, which is obviously just 1/3. And so now I can rewrite 9 to the n over 9 to the n as also 9 over 9, the entire thing to the n power, or in other words, 1 to the n. And so we'll get the series as n equals 0 to infinity of negative 1 to the n times 1 to the n. If I combine those two, we'll just get negative 1 to the n times 1/3. And so remember, in the geometric series, if negative 1 is our r value, because it's being taken to the n power, 1/3 is just a constant. So the absolute value of r must be less than 1 for convergence of the series, and the absolute value of r, which is just 1, is not less than 1, which means it will diverge. And if I plugged in negative 3, it would be the exact same thing. It would also diverge, which means that the x values that work are in between negative 3 and 3, excluding these endpoints. So this is the interval of convergence, along with the series.